Hi, here's a problem where we have an object that is in static equilibrium. And again, we're going to apply Newton's second law to solve this one. So pause for a moment, read the question. Okay, so we notice that we are asked about a clown that is yanking on a rope. And what's the minimum pulling force that clown must exert to yank his feet out from under himself? Well, the object that we're interested in is the clown himself, because the forces that are acting on him, they could cause his feet to be pulled out from under him by that rope. So we're going to focus on the clown. First thing, what is the long range force? Well, we got gravity. So F sub g points straight down, as we remember. Next, what things are touching the clown? Well, let's look at the two ropes there, right? We've an attachment point of a rope here, and we know that that means that the tension will be upwards here. So that's let's call that T1. And we've got an attachment point of a rope here, pulling away parallel to the rope there. Another one, let's call that one T2. Finally, what else is touching? There's a surface in contact with the clown's feet, right? And so we're going to have a couple forces there. We will have perpendicular to that surface. We've got the normal force. And we've also got the force, which is the static frictional force, right? Which direction would the cloud legs slip? Or what would they move if they slid? They go that way, right? So the static frictional force is preventing that from happening. It goes in the other direction. That you would tend to slide if you broke through from the surface. Next thing, we're going to go ahead and make a free body diagram of all these forces. So you can see the free body diagram that we have there, and notice how I've kind of made the length of the forces kind of balance out, because we know that this is an equilibrium, there's no acceleration. That's why they all kind of have the same length. I also plotted these two tip to tail. You can put them at the same origin if you want, but either way is fine. So now we're going to pick our XY coordinate systems. That's an easy choice. We'll use the standard one because that makes figuring out the components extremely easy here. They're already parallel to the x and y axis as we've drawn them. So let's go ahead and make our table and start to figure out the x and y components of all these vectors. So we've got a table now, and I haven't wrote down the acceleration yet, except we know that this clown is static. It's not moving, so its acceleration is 0. That makes it easy for us to fill in some values immediately here. And then we're going to look at the other things, right? So I can go through and put zeros for all the ones that don't have zeros. So let's see, FG, FN, and T1 are all on the y-axis. Therefore, it's going to be 0 here. FN is going to be 0, and T1 is going to be 0, while T2 and FS are on the x-axis, so their y components will be 0. Well, that made it easy. And then we're going to start to put in the numbers or magnitudes into the columns that aren't 0. So I know for sure that for gravity, it's in the negative downward direction for y, and the magnitude of the gravitational force we know is mg. Now for the normal force, we don't have a formula for the magnitude, but we can know that it's positive. And I'm going to just put in the magnitude variable for the normal force. For tension T1, I don't know what it is, but I know that it's in the positive y direction. And for T2, we know that it's in all of that magnitude is in the negative x direction. And for Fs, there is a formula. We can go look for Fs. If we are at the point of slipping, as it says in this problem, then we're at Fs max. And that means we have mu s Fn. So we should really be careful to write this as, actually, this is Fs max. And because of that, Fs max is equal to a magnitude of mu s times Fn. And we see that that is in the positive x direction. So we've got all that data. Now notice that we do know the weight of the clown. So in fact, the mg for the clown, remember weight is m times g, is given as 890 newtons. So we know that number. And we also know that the coefficient of static friction, mu s, is 0.53. So there's some numbers that we do have here already. There's a few things we still don't know. So we can say, okay, good, I know that, know both of those, that whole number. What don't we know still? We don't know what the normal force is or what T1 or T2 are. We're going to get these by applying Newton's second law. So let's, before we do it, one more important thing. Notice that the rope, it's all one rope in the picture, right? Turns out when you have a rope like this, the pulleys don't change the tension. So the magnitude of the tension is the same everywhere here. In fact, we can write this. Whatever the strength of T1 is, it's the same rope. Pulleys change direction, not strength of tension. And therefore, if we want, let's just call the tension magnitudes. We'll just call them T since they're the same. So that helps us out a little bit. We'll go ahead and clean that up in our table here. So I've gone ahead and removed the subscripts from the tension magnitudes, and looks like we have two unknown variables, T and Fn. If we can have two equations, we'll be able to solve for both of them. Well, luckily, Newton's second law is an equation for the x direction and the y direction. So let's go ahead and apply that, and we'll plug in our data. So for the x direction, m times ax is equal to the sum of all the forces in the x direction. We see that a is 0 in the x direction, so we got 0 is equal to, let's add up all the x forces. Well, there's only one that's non-zero. It's just, no, there's two, sorry. We would have been in trouble there. So we've got a minus t plus a mu s Fn. And for the y direction, same Newton's second law. Whoops, that should be a y there. And, oh, okay, that's nice. Got a 0 there. I'm going to add all these up, put them onto that side. So we're going to get a 0 is equal to minus mg plus Fn plus t. And at this point, it's all math. We're going to plug in our numbers and we're going to solve this stuff. So, for example, we can say that t is equal to mu s Fn. I'm not going to plug the numbers in yet, even though I know mu s. Over here, I can say that, let's see, let's solve for t over here. T is equal to, I got to add the mg to one side, and I got to subtract the Fn from the other side, right? Well, let's go ahead and just plug this t into the t over at the other equation, right? Two equations, two unknowns. We're going to solve this thing. So mu s times Fn is equal to mg minus Fn. Let's bring the Fn to the other side. So mu s Fn plus Fn equals mg. And finally, we'll factor out the Fn. Fn, I got a mu s plus 1 equal to mg. Let's divide by both sides, and we're going to end up with mg is equal to mu s plus 1. And so we just plug our numbers in there. We know that the magnitude of the weight mg, 890 newtons. Remember, weight is in newtons, mass is kilograms. They gave us the weight, divided by 0.53 plus 1. We'll put that into our calculator and we'll get our answer. And this comes out to 582 newtons. So we just figured out the strength of the normal force. Now to get to tension, that's easy. Once you got the first one of the two equations, the second one, you just go ahead and plug it in. So we got mu s times Fn. We know that mu s is equal to 0.53, dimensionless, and the normal force we just calculated 582 newtons, and when we put that into our calculator, we get an answer that's equal to 308 newtons. So that is the tension in the string or the rope, everywhere in that rope. Now if he pulls just a little bit harder, that's going to cause the tension to increase, right? Because his pull strength on the rope is equal and opposite to the tension in the rope by Newton's third law. If that happens just a little bit stronger than 308 newtons, he's going to cause the friction, static friction, to break free and he'll slip. And so another example of how to solve a dynamics problem, Newton's second law. Again, the steps: draw your picture, identify the forces, draw a free body diagram, figure out the x and y components, use a table to organize your work, and then go ahead and input your data into Newton's second law in the x and y directions. You can put your numbers in first or later. I like to do it later, and then you'll get all your answers there.